Hello, everyone, and welcome back to this week's topic where we're going to be talking about analyzing the code and the algorithms that we write. Today, we're going to answer a deceptively simple question. Why do computer scientists need to analyze algorithms at all? What happens if we are running a search algorithm? If you double your data, should your program take twice as long? Or should it take 100 times as long? Should it take more time at all? That difference is basically the whole game that we're talking about today. We've written lots of programs this term, and at times I've even measured the code execution and encouraged you to do the same. I hope you actually tried it, although you probably didn't. Maybe you measured how long it took to run with a stopwatch on your phone, or maybe you formalized it a little bit more and you used like the system dot nanotime or millitime that we've used. More likely, you probably just watched the output appear and sort of felt, oh, that maybe took longer than last time or something like that. But here's the problem that we're actually going to try to solve today, which is that timing like this, timing really in general, can lie, and they lie a lot. So we need a better way to compare our algorithms, and one that doesn't depend on the laptop that we're using and how fast it is, or what data set that we're using. And this is where analysis of algorithms comes in. So let's start with the obvious question, which is why can't we just time our program and compare? So let's imagine for a second that I tell you that I am writing a linear search program. Let's go ahead and write that down. Linear search. And here we can see I have an array and I've got a target value that I'm going to be looking for. Now imagine that I tell you that it takes maybe 2 milliseconds to run on my computer, no time at all. Then you go and try to run it, and your laptop might be older than mine or newer, or it could be running 300 Chrome tabs that are all open at the exact same time. You could have a different battery that could be in a different mode, like a low power mode or a high performance mode, and that can throttle the CPU. And even though Java has an environment that allows us to hope for reproducibility, and we get pretty close to consistent reproducibility, it also can have warm-up effects because there is also a just-in-time compiler that will optimize as your code is going. So the memory layout of your code can change every single run. This means that two students could run the exact same piece of code and get time measurements that might differ by 3 times or even 10 times as long. It's kind of like reading a book. Somebody might be a really fast reader, somebody else might be a really slow reader. You can ingest the same information, but at the end of the day, different people might read at different speeds. It's exactly the same with computers. We need to find a way to analyze this and have a much more stable answer rather than just seconds on a clock. So instead of measuring how long does it take for this to run on my laptop, we're going to measure something that stays the same everywhere. We're going to ask ourselves the question, how many steps does the algorithm do? All right, so let's start talking in steps. I've already drawn an array here. We'll just pick it up and move it over here so that we can sort of start all in the same place. And let's just label everything so that we know what's going on. 3, 4, 5, 6, 7. This gives us an array of size 8, so we'll say n equals 8. So let's suppose we're doing a linear search, and you've seen this before, where we're going to look at each element until we find the target. Let's quickly write up the code for that, and I am going to write the actual code that should actually run. At this point of the course, this code should feel like second nature to you. When we're talking about comparing steps, we're talking about every single time that the algorithm has to go and actually access memory. Now, there are different ways of counting steps, and when you reach the next course, you may find yourself including counts in the beginning, such as these lines of code here. But for right now, what we're talking about actually going into heap memory and doing a comparison. Right here is where we see we're actually going into heap memory. We're going to go follow that reference of A, get the value at position, and retrieve it. For our purposes right now, with this very shallow explanation, this is what we're going to consider a step. So what that means is every single time that this line of code runs, we want to count one step. We could even do this in code by adding a variable like int step starts at 0, and then right before we do this comparison, we can just increase our counter to help us keep track of how many steps are actually being taken as part of this algorithm. So This is going to be completely independent of the hardware, the time of day, the laptop, the battery, all of it. This is a pure counter of how many times we run that line of code that I've boxed in red. If two algorithms do two different numbers of steps for the same input size, this can tell us which one will scale better. Seconds really only tell us which laptop was faster. So for example, with our example up here, we have our input size n. We can see that if we were looking for target 31 as before, the number of steps that would be taken would be first, we'd look here, 1 step, then here, 2, 3, 4, 5. It would have taken 5 steps to find 31. Now, this is even just the beginning. Step counting is just the start. Like I said, some people might even count these steps also as part of their final value. Even a step count for one input size really doesn't tell us the whole story. Hopefully you're already realizing that. What if instead of looking for the target value 31, I was looking for the target value 0? Now, for this same input size of n equals 8, we find a step count of 8. If we were looking for the target value of 7, we would find it in the very first spot, making our step count 1. We can see that having one data point isn't going to be enough to give us a full picture of an algorithm's efficiency. What matters is how the step count grows when our data grows. And that's the key idea behind analysis. Let's compare two very different behaviors. Let's start with an algorithm that does about n steps. N-step algorithm. And let's compare one more. N-squared step algorithm. I'm going to draw two different things. First, I'm going to draw a loop that goes through all of our data once. So for example, if we had a method, doesn't really matter what it does, and our data array right here for int I equals 0, I is less than data.length, I++. Perhaps what we'll do is we'll do a system.out.println, and we'll just print out whatever's in data at each position. We can see that this is an n-step algorithm, because where n is the length of our data array, we are going to go through the entire data array and print out every single element. Now on the other side, in this n-squared stepped algorithm, now I'm going to draw nested loops that will go through our data again and again. So for example, a method with that same integer array data, only this time for each count of data I++, we're going to have an inner loop that goes through the data as well. And this algorithm here, system.out.println, can also print out data at I. So this algorithm over here would print each element once. This algorithm over here will print each element n times. Let's draw a table that will actually compare this data here. And let's start with our first algorithm. Let's draw a table with 3 columns, n being the size of the data, the linear steps that it took, so linear being 1, and our nested being 2. So these are going to keep track of the number of steps. Right now I'm showing you a table with 4 elements in it. So we'll put 4 right there. How many steps are we going to actually do when we run our linear algorithm? Well, if we come back to our linear algorithm and see where we're actually accessing that data at I, we do it exactly 4 times because there are 4 data points, and each time we print it out once. So let's go ahead and put a 4 right in here. Now let's look at the other one. Let's look at our nested example, which is over here. Now what we see happening is when I is 0, we're going to print 4 times. We're going to print 9 4 times. And then when I is 1, we're going to print 18 4 times. And then when I is 2, we're going to print 2 4 times. And when I is 3, we're going to print 6 4 times. So we actually end up printing 16 numbers. We access each data point 4 times. That's 4 times 4. So we get 16. Let's grab another data set. Let's add on one more data point right here. So now instead we have 5 values. Once again, we can see right here that our for loop will go through every single data point, printing each value once. That's going to leave us with 5 steps. And once again, if we come and look over at this one, before we had 16 steps because it was 4 times 4, or 4 plus 4 plus 4 plus 4. But this time we actually have 5 runs of our outer loop, which means 5 inner loop runs for each one as well. This ends up being 5 times 5. So we get 25 over here. And let's just add one more for good measure. Let's add on one more data point. And this will be n equals 6. Once again, we know our algorithm, our linear algorithm, I should say, takes n steps because we print each data point once. And this one grew again, where every single data point got printed n times. So 6 times 6 gave us 36. So what we see happening here is when, for example, n is 10, our linear gives us 10 or n steps. But our nested is actually going to give us 100 or n squared steps, right? Because what we found was it was n times n. When n is 1,000, we can see that our linear algorithm will take 1,000 steps. How long will it take our nested algorithm? Well, that's going to be 1,000 times 1,000. It's actually going to be, whoops, I can write. It's actually going to be about 1,000,000 steps. So even when we saw these smaller numbers, yes, an increase, but maybe the difference between 4 and 16 or 5 and 25 didn't feel very big. The difference between 1,000 and 1,000,000 starts to add up really quickly. You'll notice that in these two different scenarios, I didn't do anything to the hardware, right? I didn't change the computer. I didn't change my algorithms. I didn't change the battery mode. All I changed was my n value, the size of my data set. This explosion down here in work, as the data set size grows from 1,000 all the way up to 1,000,000, comes from the shape of the algorithm, not the speed of your computer. And this is why we pay so much attention to these growth patterns in our code. Let's go ahead and draw a graph. If we were to label our graph, so 0, 1, 2, 3, 4, 5, and so on. 0, 1, 2, 3, 4, 5, and so on. What we can see happening with our red line here is if this is keeping track of our n values, and this is keeping track of our step values. Let's look at the red line. When n is 1, our step was also 1. When n is 2, our step is also 2. And when n is 3, our step can also be seen here as 3. So this straight line right here, that wasn't very straight of my highlighter, but this straight red line right here, that is representative of an algorithm that does about n steps. Now when we look at the purple line instead, I don't actually have a purple highlighter, but that's okay. We can see that just between 0 and 1, we see this really steep increase in the number of steps that are occurring. This purple line right here is supposed to be indicative of an algorithm that does about n squared steps. If I upgrade my laptop, let's say I get a faster CPU or more RAM, both lines might shift downward, meaning everything runs a little bit faster, but the shape itself will not change. The linear line right here stays relatively mild, and the quadratic curve will continue to shoot upwards earlier. No amount of CPU improvement is going to change that fact. The fact being that quadratic growth will always overwhelm linear growth as n gets bigger and bigger and bigger. That's what we saw happening right here. This is our linear growth, and this one right here is known as quadratic growth. And as n got larger, like this, we could see that this just continued to overwhelm the linear growth, the linear number of steps. This is the reason we actually analyze the scalability of our program, because scalability will beat speed every single time, regardless of how fast it is in these early steps. As we start to increase our n, what matters is is the algorithm that we made scalable? Can it keep up with N growth? And keep in mind that modern data sets are huge. We're not talking about a few hundred or a few thousand items, not even necessarily a few millions. These are billions of data sets and billions of data points. If your algorithm is going to double in runtime every time that the input size doubles, maybe that's okay. It might not be, but it might be just fine. If your algorithm multiplies its time by a factor of 100 when the input doubles, that's actually unusable. Analysis of algorithms gives us the vocabulary and the tools that we need to spot which algorithms can survive the real-world scale and the real-world environments. So what we've established is that using a stopwatch to time our code or even using built-in timing is honestly not very reliable. We need to be doing things like counting steps to give ourselves a hardware-independent comparison scale. The real story is how the work grows with input size, not a single data point. And some algorithms might scale nice and gently, while others can just explode. In the next video, we're going to introduce some simple notation that computer scientists use when they talk about these growth shapes. Thanks everyone, and I'll see you in the next video.